Last time we left off with the death of stars, and we talked a little bit about white dwarfs, and we talked a little bit about neutron stars. But of course, when we get to the biggest and baddest of stars that are out there, we end up with black holes, and that's often a very interesting topic for many people. When they talk about astronomy, they're often talking about solar system exploration, they're talking about life on other planets, but quite frequently they're also talking about black holes. I remember when I was a child, there was a Disney film called The Black Hole. It's rather interesting. It still stands up pretty well in terms of its sort of cinematography and the special effects that it had. A little bit of a cheesy storyline, but that's okay. But I remember in particular because it was the first Disney film that had a PG rating. And that was significant, not because there was anything obscene or anything that might be dangerous to children, but simply because the idea of a black hole was considered to be more of an adult idea. And they didn't know that children would actually relate to it very well. I related to it just fine. Of course, I'm interested in astronomy, so there we are. Black holes have been mysterious for a very long time. They still are in different respects. But it's only really been in the last half century that we have understood what they could be gravitationally, what they could be physically, and have begun to understand what we can do to find them. Because by definition, they don't emit any light. Now we'll see with Hawking radiation in just a short while how there are bits and pieces that fray at the edges of that theory. But one of the ways in which we know a lot of things in astronomy, and black holes are significant in that regard, is not by the things themselves, but by what they do to other things around them. Here is a picture on the left and a sort of artist recreation on the right of what the black hole in a place called Cygnus X1 would look like. Now, Cygnus is a constellation. X means it's an X-ray source that we're seeing it, and 1 means it's the first X-ray source we found in that constellation. It is generating a huge amount of X-rays, and in large part that's because as material falls into the black hole, it is generating lots and lots of energy around the black hole. And one of that energy sources is the X-rays that we're seeing from it. This black hole is part of a binary star system, meaning there are two stars that are spinning around together. And as we've discussed earlier in the semester, quite frequently when we have binary stars, one is going to be larger than the other, one is going to outlive the other. In this case, the larger star collapsed into a black hole, and it's close enough to its companion star that it's pulling material off. And as that material spins around, we get huge amounts of energy formed from the processes there, largely the friction and the heat that's being generated as things are swallowed into the black hole. And it begins to glow, and it's glowing with X-rays. So one of the things that we are trying to do right now is to discover more and more about gravity waves. We have the LIGO, observatories. I hate to use the word observatory because when we think about observatory, we think about the things on the top of Mauna Kea in Hawaii, or we think about the Kirkwood Observatory. These are of a different sort, and we'll talk a little bit about them in a little bit. But one of the things that they're doing to find gravity waves is we're looking for collapsing processes around neutron stars or black holes. Because as these powerful objects gravitationally collide with each other, they begin to generate all sorts of energy, including gravity waves. That anything in our solar system putting out gravity waves is going to be so lacking in power, we wouldn't be able to detect it even if it were right in front of us. What a black hole is it is an area of space around a supermassive star that has run out of energy and it's collapsed in on itself. And as we talked a little bit in the last lecture about white dwarfs and neutron stars, white dwarfs sort of hold themselves up by packing the material in further and further until the electrons themselves push out. Neutron stars, the electrons actually get pushed into the protons that are there and they become neutrons, and there's no space between the neutrons. When we get even higher, when we get up to maybe 10, maybe 20, the boundary for this is still under debate. But when we get up to certainly 30 times the size of our sun, there's no force that's going to keep that material from falling into itself if the energy in the core has stopped running, if the fusion process has stopped running. So it just collapses further and further and further in. It becomes a pinpoint, a tiny, tiny point, and they become infinitely dense and zero radius. So a black hole would actually fit between my fingers, but the area around it is still being influenced by the gravity. If I have a rock that's 1 pound, it has a certain amount of gravity. If it was the only thing in the universe, it would still have gravity. So the larger and larger and larger you get, the more and more gravity you get. Well, these are really big things in terms of gravity. We have Albert Einstein, as we've talked about in different times in our semester, to thank for the mathematical and geometrical concepts that allow us to go into understanding black holes, although, like many people, he was wondering if these were actual things. When we're talking about gravity, gravity is in fact a tricky concept. The Earth is pulling us down, and everything that goes up must come down. That's an old adage that's there. But in fact, we can have different ideas about how gravity works. If you are moving, things tend to change along the way. And we can think about the elevator experiment. If you're just sort of standing in the elevator, and you happen to be standing on a scale on the elevator, as we sort of see in our first graphic here on the left, and the elevator is not moving, you're going to have your normal weight. I'm unfortunately 225 pounds here outside of the elevator. I'm 225 pounds on the elevator. But if the elevator is going down, you sort of feel a little bit of a rise. You're going to rise just a tiny bit, and the faster the elevator is going down, the more you're going to rise. You look over at the scale and hey, you weigh a little bit less. If you're going up, then you sort of feel that sort of extra tug. Things feel just a little bit heavier. Again, if it's faster, you'll get more of a tug. And you notice on the scale over here that your weight has gone up. If the cable snaps and the security apparatus isn't working on the elevator and you are in free fall, you actually have no weight because you're not on the scale anymore. So as it accelerates up or down, it will change the weight. So gravity acts like a type of accelerant, or acceleration. I shouldn't say accelerant, that's a chemical kind of thing. As we're looking here, notice as the people fall, the ball is also falling along the way. So as you are throwing it back and forth to the two of you, and we're going to hope that there's a trampoline down here so that they can bounce back up and not just crash into the ground. But between the two of you, it'll look like the ball is going straight. But any observer outside, as we are going to notice that the ball is actually also curving around as it goes down in response to gravity. We notice that people on the space shuttle or in the space station, as we've talked about before, they are in free fall, and that's why things are floating in there. It's not that there's no gravity in space. If the space station or the old space shuttle or any other spacecraft are actually in space at any one point above the Earth, say it was in what we call geostatic orbit over Houston or over London or over a particular place, then it's actually still going to have gravity. It'll have less than it has on the surface, but it'll have a significant amount of gravity. The reason why there's no gravity inside of these, apparently, is because they are in free fall, just like our elevator person over here, who seems to have no apparent weight. As we do different experiments, we can actually see the way that things will move along. As you see here, as a spacecraft like the space shuttle orbits around the planet, one of the things that it will be doing is it will be following a curve. It won't actually be going in a straight line. So we might actually expect, if we were to beam light out, that in fact it would be going in a different direction, because the light waves would be going in a straight line, than the shuttle itself. But what we actually find is that the light curves around in the same path, because what's happening, in fact, is we have a curvature. This acceleration due to gravity is actually an acceleration due to space and time. Now, there are different people who have come to our rescue when we're looking at light, as we talked about once upon a time. Newton and Huygens talked about, is it a particle, is it a wave? We figured out that in fact we have a wave-like particle that is what we understand light to be. It's an electromagnetic force. What we have is X-rays and gamma rays and ultraviolet waves and light waves, what we call Roy G. Biv light waves, infrared radio waves. All of these different kinds of things are in fact related to each other. James Clerk Maxwell taught us that. And Einstein told us that it really depends upon where we're looking as to what we're going to be seeing, and that your position as an observer is crucial. Because what we see, sort of going back to our people who are falling down, if you're one of these two people, you'll see the ball going back and forth. But if you're outside, you're going to see things curving around. That's also true when we look at a boat, for example, as we have here. You're watching the boat. Relative to the water, it seems to be going at a certain speed. But if you're on another boat somewhere, you're going to be watching it, and your mind knows it's going at a certain speed. But if you're going at the same speed, it's going to stay stationary to you. The river itself is going to be affecting the speed. The velocity of the engines of the boat are going to be influencing the speed. So just how fast is the boat going? Well, when we were trying to figure out how fast light was going and whether or not it was being affected by a kind of stuff that's in the river, we don't have water, but there was the idea of ether. There was an idea that if light is going in a particular direction or another direction, it might be going a little bit faster, a little bit slower, because if the ether is flowing in this direction and the light is flowing in this direction, it's going to slow it down. Just like if the boat is going in this direction and the light is going, or the water is going in this direction, and in the opposite direction, it will slow it down a bit. That's why planes, as they fly towards Los Angeles, they actually have to fly against the wind. It often takes longer than if you're flying from Los Angeles. It often takes a shorter amount of time. Einstein figured out that there is no ether issue here along the way. As we are trying to figure out where we are in space and time, it really is a calculation of both space and time. We don't just say we've gone from point A to B, as we see here in this. We have to go from A to B in a certain amount of time, because we don't get there instantaneously. If I'm going to Indianapolis, let's say it's 60 miles away, well, I've traveled 60 miles, but I've also traveled that 60 miles in a particular amount of time. It may take me an hour to get there. It may take me 2 hours to get there. It may take me a day to get there, depending upon how fast I'm going. So we often think of distance as being a part of our three-dimensional world, because we're going up or down, we're going left or right, we're going forwards or backwards. But in fact, in this kind of grid here, the space-time diagram that I'm showing you, we can treat distance all as one characteristic, all as one plot line. And then we have time going on the other. If you're just sitting somewhere, not moving at all, in fact, and we'll discount the fact that the planet's spinning and the stars are moving through the galaxy. If you're not moving at all, in fact, you are still aging. You are still going through time. And that's what this would represent here. So my trip to Indianapolis would actually be sort of stop, start, stop, start, stop, start, because there are all sorts of stoplights in between. So it wouldn't be nearly this smooth along the way. But even if you're just sitting there, you're still moving through time. You're going through the vertical axis. So what Einstein said is we need to put this time element into the mix when we're trying to figure out how fast or slow anything is going along the way. So he developed the theory of relativity. What you see is relative to where you are, with one major exception. The speed of light, wherever you are, is always going to be the same. So if you're in the space shuttle going 16,000 miles an hour, if you are on a particle of light that's going almost the speed of light or at the speed of light, the speed of light doesn't change along the way. This might sound like, well, that just makes common sense, but view it from this perspective here. If I'm in a plane, I'm going 600 miles an hour. Let's say 600 miles an hour is a fairly typical jet speed as it's going along in the sky. If I have something in my hand, like a ball or something like that, and I throw it down the aisle, and let's say that the stewards who are on there are happy to catch it. I'm not just throwing it to be obnoxious and then they get mad and call security. To me, that ball is probably going to go 50, 60 miles an hour. I'm not going to throw a fastball or anything like that in the plane and try and break the windows or anything like that. But if I am standing down on Earth watching that ball is actually not only going the 50 or 60 miles an hour that I threw it, but it's also going the 600 miles an hour of the plane. So my radar gun on that ball would be 650 miles an hour or so. But from the plane, if I had a measuring device watching it, it would be only relative to my motion, only 50. And that's not unusual. That makes perfect sense to us. But light doesn't work that way. Think about this. If you are sort of going in a train, and we don't have a lot of trains here in the United States, unfortunately, but we can sort of think about it in this way. Let's say you're throwing something back and forth, back and forth. The train itself is going in a particular direction. And as the train is going in that particular direction, you would think that that mailbag that is being thrown here in the picture would also pick up that velocity. And the truth is, it does. But you don't feel it. The person who's going to catch it over here doesn't feel it coming at super speed, because she's moving and he's moving and the bag is moving all together with the boxcar. So if you are standing outside trying to catch it, then it's going to hit you like a ton of bricks with this kind of velocity here. But if you're on the car, you're only going to get the added velocity of how he throws it, rather than the full weight of everything that's there. If I throw something straight up, it'll come straight back down. But as the car is moving, in fact, it's going to curve from the perspective of anyone who looks at it from the outside. So see, this one's going to hurt. This guy is going to get the bag not only with the velocity that the guy throws it, but also the velocity of the train going. So if you're going to catch things like this, the way to catch them is to actually be standing on the other side of the train and have him throw it backwards. That way you reduce the velocity along the way. So when we're dealing with these kinds of things, we're dealing with paths. Everything is moving in a path. That bag is moving in a curve. If, as I told you before, if you throw something straight up and down, for you, your perspective on the train, it looks like it's going up and down. But as the train is going, if I'm standing off to the side, it will look like it's curving. If we're standing on a two-dimensional sheet, let's say we're the ant here who's walking along this rubber sheet, it just goes straight across. But if there's something in the way, like a paperweight that's creating what we would consider a simulated gravitational force, then the ant seems to still be, from the ant's perspective, going in a straight line. But from our perspective outside, we're watching it curve. It's warped a little bit. And that's what happens with planets and stars and anything that has gravity. Everything that goes around our planet is being influenced by the gravity of our planet. Everything that goes around the sun is being influenced by the gravity of the sun. One of the things that would happen if we're in free fall is that we're going to be sort of counteracting that force, because we are actually in a different frame of reference. We're not at rest, we're actually in motion. So when we're looking at a free fall, we're in what would be considered inertia. So I would just sort of float. I wouldn't float in any particular direction unless something was pushing me in a particular direction along the way. So we live in a curved space-time environment. The curvature around the Earth is not very severe, is not very sharp. That's why we have the gravity that we have. It's more than there is on the moon. That's why you weigh less on the moon. It's more than there is on Mars. You would weigh less on Mars. It's less than would be on the sun. You would weigh a lot more on the sun. It's less than on Jupiter. You would weigh more on Jupiter. So what's happening is the space-time curve around anything depends upon how large a mass it is. Now, one of the ways in which this theory was tested was Mercury's wobble. For a very long time, there was an idea that there might be a smaller planet somewhere inside here called Vulcan, because as Mercury goes around the sun, and remember, planets don't go around in perfect circles, but as Mercury goes around the sun, it actually shifts. And you can sort of see this almost like a spirograph as it's going around and around and around. These perturbations have been known for a very long time. Part of the reason for them is because out here, beyond Mercury, we have planets like Venus, Earth, Mars, Jupiter, Saturn. They all have gravity too. So they're tugging a little bit away from the sun. The sun is tugging towards itself, obviously, in terms of gravity. So Mercury gets tugged and pulled. It's a very small planet. But Newtonian gravity, all the calculations that they were doing for that, only accounted for about half of what we would see or what we should see. The idea of the other planet that's in there was to make up for the fact that it was being pulled more than what we could calculate. We never found that planet. There was one astronomer who claimed that he did, and there were a couple of amateurs who also thought they might have seen it. But we now know that, in fact, the reason why this is happening is Mercury is close enough to the sun where the gravitational well, the curving of the space-time around the sun, is actually pulling it in different directions. And it causes it to have this, what we call the perihelion shift, or the wobble that we sense. Now, as light comes by the sun also, it will also be affected by this wobble effect. It will be affected by the curvature that's there. And this was another test of Einstein's theory. If we have stars that are behind the sun over here, and the light comes by the sun, well, during the daytime here on Earth, we're not going to see them. But what happens if we have an eclipse? The sun is blocked out and we can now see the stars behind it. So Einstein predicted, and it was then later confirmed, that as the light from the stars behind the sun come through the gravitational field of the sun, the space-time warping of the sun, they would in fact be bent. The light gets bent. It actually goes around the curve. So this light from the star, if the sun wasn't here, would just keep going straight across like this. But because it warps around, it makes it appear to us to have shifted. It's in a different location. How can we tell that? Because 6 months from now, the sun's going to be over here on the other side, and we're going to see these stars at night. And they're going to be in slightly different places than they were when we saw it through the sun's gravity. Here we can see, again, this is called gravitational lensing. If we're just looking at the star from the Earth, we see where the star is on the grid. But as the sun comes through between us, The light from that star, which would normally come in this direction, gets bent around the sun, and now the star looks like it's moved along the way. We can actually test this with different kinds of gravitational lenses. We don't just have to wait for solar eclipses, but this was the big test. This was the big test in 1919. We also can verify this because as our satellites are up above the Earth, as I mentioned before, there's less gravity up there. It's not that there's zero gravity, there's less gravity. The further up, the further away from the center of gravity you get, the less gravity there is. So as they go up further and further, one of the interesting things that happens is that the clocks run at a different rate. The closer you are to the center of gravity, the slower your clock will seem to run. The further away you are, the faster it will seem to run. And we actually have to put in adjustments to our satellites because even though they're only a couple of 100 miles up there, they're far enough away that their clocks run differently from our clocks here on the ground. And of course, if you're losing a couple of seconds, that doesn't seem like a lot, but you add a couple of seconds and a couple of seconds and a couple of seconds, day after day after day after day, and suddenly you're driving off the bridge and driving down a road that doesn't exist because GPS doesn't know how to tell you where to go. We have to make these adjustments on a regular basis. There are time delays from the different probes that we've sent out into space. When we launched the Viking probes, they landed on Mars in the 1970s, and they communicated with us as Mars went around the sun. Sometimes Mars would be behind the Earth in a position we call opposition, so the beams, radio beams, the communication beams would come right to us, no problem. But sometimes it would be on the side, and sometimes it would be actually behind the sun. And as those beams of radio waves, which are also electromagnetic waves, would go past the sun, what would happen would be that they would be delayed. There's a little extra lag time there because the curve is longer than a straight path. It's the shortest path according to the wave, but it's not the shortest path if we were to look at a Euclidean kind of thing. Now, what happens around a black hole is the curvature becomes complete. It becomes what we consider to be infinite. And so as light tries to follow a curve to get away from the black hole, the black hole gets denser and denser, the curvature around it gets sharper and sharper until finally nothing's getting away. And as we go closer and closer to it, different things will start to happen. As I mentioned before, look at this. This is called spaghettification. If I'm standing on the event horizon of a black hole, my head is going to be further away from the black hole than my feet. And so gravity is going to act on my body in different ways. And as I get closer and closer to the black hole after I've slipped through the event horizon, and we'll talk about what event horizon is here in just a moment, as I slip through that, my body's going to get longer and longer and longer. It won't be a lot of fun. One of the persons who we can thank for the term black hole is a guy named John Wheeler. He was one of the ones who popularized it, not necessarily the first guy to ever use the term or come up with the concept. In fact, we have concepts going all the way back a couple of 100 years to a philosopher named Immanuel Kant, who was also thinking about a surface that's so powerful in gravity that not even light can escape from it. But John Wheeler here is one of the ones who figured out some of the dynamics of a black hole. As we stand here on Earth, if we send light out into space, which we're doing with streetlights and other things and causing light pollution, the light goes off in different directions. But if we have a really massive gravitational force, some of that light might be bent. And the more of a gravitational force that we have, the more bending takes place. So when we are at the event horizon of a black hole, all of the light gets bent back down completely and can't escape. And that's why we call it an event horizon. We can't see any events that happen inside the horizon. See, just like if you're standing on the ground and looking out towards the horizon, you can't actually see anything that's beyond the horizon. Well, we can't see anything that's beyond this horizon. We can't see any of the events that are taking place inside. Now, this guy, Schwarzschild, was one of the first ones to figure out how a black hole's event horizon relates to how much stuff is in the black hole itself. And unfortunately, as you can sort of see here, it's a rather tragic story. Schwarzschild was a person who was drafted into military service during World War I. And he did a lot of calculations while he was sort of just waiting around for something to happen, because warfare is quite often sitting around and waiting, and then lots of terror in just a couple of minutes. He actually died of an illness that he contracted, and it was largely due to the unsanitary conditions around what was being fought during the war. But in his spare time, he did math. This was his hobby. This was also his profession, but it was also his hobby. It's a pretty good thing when you can merge the two together in different times. But what he said was, basically, the larger the black hole, the further away the event horizon is going to be. And he came up with calculations to verify that. So what we have essentially is, with a black hole, with any particular thing, there's going to be a little bit of a curve around the Earth. As you see here, there's going to be more of a curve around the sun. But with a black hole, the curvature becomes infinite. So the way we sort of depict that is we can't really go any further than this. We just know it keeps going down and down and down. Now, one of the interesting things about the black hole is, notice here, here's the Earth, here's the Earth. If we had a black hole that somehow managed to be the same mass as the sun, the Earth would still just be going around here, as it normally would. It's not actually going to pull it with any extra oomph. You don't get that extra oomph until you're right at the event horizon. But you'd have to be going faster than the speed of light to get away from it. And of course, that's what Einstein said you can't do. So right now, we think that any star that is 20, 30 times the mass of the sun becomes black holes. There aren't that many of those stars out there. As we talked about stellar populations before, remember there's only one major star for a collection of mid-sized stars and for hundreds and hundreds of minor stars along the way. What happens, of course, is that the fusion processes in the center cease. The weight of the mass that's still in the star itself begins to fall in on itself. Part of the mass is given up in a supernova explosion. So at the center of a lot of supernova nebulae, we will find a neutron star or a black hole. That pinpoint that's at the center, we call that a singularity. And the singularity is because if you ask how large something is, you're talking about how wide it is, how long it is, how tall it is. Well, this has 0. This is 0 times wide, this is 0 times long, this is 0 times tall. This is a 0. Everything is crunched into literally nothingness. So that's why it's infinite in its density. But in terms of the size of the black hole itself, the center of the black hole, that is at a mathematical 0, and we call that a singularity. But here's our guy Schwarzschild. What he figured out is the more stuff that's in this singularity, the wider the area around the singularity that light can't escape. So if you're out here just beyond, you can still escape. You'll be curved quite a bit, but you can still escape. Once you hit this area, you're trapped. You have to go faster than light to get away. And the more stuff that's in the singularity, the bigger this area becomes. And so the event horizon is the point of no return. And the distance between the singularity and the event horizon, we now call the Schwarzschild radius, because he's the guy who figured it out along the way. And the formula for that is this little thing down here, which looks rather messy, but it's actually very simple to understand. The radius, that's the R, that's our line here. We put the S there because it's a Schwarzschild radius, is 2 times our gravitational constant, that's just the sort of thing we've known since Newton's time, times the mass that's here in the middle, divided by the speed of light squared. So it's actually a very simple formula to calculate with. We don't have to get into all of the fineries of all sorts of advanced math. It's really, in fact, that simple. So it's hard to find a black hole if it's just sitting out there doing nothing. Fortunately for us, lots and lots of stars, maybe as many as half of all stars, are part of binary star systems. So when we have a supermassive star that's part of a binary system that turns into a black hole, quite frequently we'll start having this mass exchange. And we talked about that with a couple of different stars in earlier lectures. Algol is one of the key ones that shows a mass exchange. The nature of a black hole changes a bit if, in fact, there are a couple of other things happening. That Schwarzschild calculation that I showed you before, that equation that I showed you before, works if we have a black hole that's just sitting there, that's not spinning and doesn't have any electrical charge. But most things are spinning, so that throws our calculations off just a tiny bit. And as they are spinning, and as they may have an electrical charge, they change the nature of the stuff that's around them as well. So we end up getting, as things are falling in, and we end up getting, as things are spinning around, different kinds of interesting effects that will happen. If you are near a black hole, you would be able to see things behind the black hole in the same way we were able to see things behind the sun during a total eclipse. So one of the things that happens is black holes, while they themselves might not be visible, will sometimes give us this gravitational lensing to see what's behind. What will sometimes happen is we'll see multiple copies of the same thing, this light from the stars coming in both directions around it. And so sometimes we'll actually have a ring around the black hole, and that's sometimes called an Einstein ring. So as you are going into the black hole, of course, gravity is pulling on you, just like an acceleration would seem to be pulling on you. As you're getting closer and closer, as I mentioned before, your feet are closer than your head, so you're going to end up being stretched. That's our spaghettification that's happening there. We have verification in multiple different ways of black holes at the center of our galaxy and other galaxies. In fact, the big black hole picture that came out just last year was from a supermassive black hole at the center of a supermassive elliptical galaxy. And that has actually billions and billions of times the masses of our sun in it. Our supermassive black hole in our galaxy is actually pretty tiny by comparison. It's only 2 to 4 million times the size of our sun, rather than billions and billions and billions. So what we see is that there are two real categories of black holes. We have some that are about the size of our sun to maybe 100 times the size of our sun. We call those stellar mass black holes, and those are what happen when a star dies and collapses in on itself. Then we have supermassive black holes, and they have 1 million to 1 billion, perhaps as many as we see here with our 10 to the 9th. We can get perhaps as much up to multiple billions, and perhaps even, although it's speculated that not quite to the trillion mark in terms of how much it is. But we could have one black hole at the center of a galaxy that could be larger than some smaller galaxies in terms of mass. One of the first ones that we've discovered that we sort of highlighted this is likely to be a black hole, so I mentioned at the beginning of the lecture, is Cygnus X1. Again, it's in the Cygnus constellation. It was discovered by the Chandra X-ray Observatory. I mentioned in the previous lecture a guy named Chandrasekhar, who was a mathematician and astronomer of great note. One of NASA's great observatories was sending up the Chandra X-ray Observatory. And that's necessary for us because our atmosphere blocks almost all X-rays. So the only way that we know what's happening out there X-ray wise is by getting above the atmosphere. Well, as material is falling into the black hole around Cygnus X1, it is being accelerated, it is being heated during the infall, it's being rotated around, and we're getting a lot of friction. Things are falling into the black hole, and things are being generated because of all of these processes that are here. So these galaxies and these black holes, either next to stars or in the center of galaxies, can be rather violent places to be. At the center of almost all galaxies are supermassive black holes. What we have sometimes is an active galactic nuclei. We'll talk about that more in our later lectures. Sometimes they're rather dormant. Sometimes we have black holes, like at Cygnus X1, that are putting out lots and lots of material, lots and lots of energy as material gets drawn into them. Then there are other times where we will have things that are fairly dormant. These jets of material that can be thrown off and various energy sources can be going really, really fast. And they're also often called microquasars. Quasar is a word that is developed from quasi-stellar object. They're radio sources. The first quasars were radio sources that we didn't know what they were. So we called them quasi-stellar objects. But one of the interesting things that happens around a black hole, whether it's a smaller one or a larger one, although as we get larger and larger, this effect happens more and more, we get what's called frame dragging. And what it does is it sort of changes the way that time and motion is acting on the material as it's going around. It's literally pulling on the space-time itself as it goes around and around. It's a pretty heady concept. But one of the ways in which we are looking for these is with the LIGO facility. As I mentioned earlier in the lecture, I didn't really want to call this an observatory, because when you look at this, this doesn't look like your typical observatory. But what we have are these detectors that stretch for miles. It says they're 4 kilometers long, which means they're going to be over 2 miles long. And what is happening inside of these is that there's one here in Louisiana, there's another one in Washington State, long, long way away. They work in tandem with each other. Is that as gravity waves come across this, it will come across the one that is in the horizontal direction differently from the one that's going across in the vertical direction here. And we can measure the difference of what's happening there, and that gives us an indication of what the gravity waves are like. We need really powerful gravity waves to make any kind of signal at all that's detectable for us according to our current technology. And so what we look for are when we have either neutron stars or black holes that are spinning around each other and merging together. We have right now a couple of black holes and a couple of neutron stars that we're investigating that may be, in fact, about ready to collide with each other. And as they get closer and closer to each other, they are sending off energy. As things actually spin into each other, it changes the net effect of what's happening in the system, and it either has to absorb energy or shed energy. And one of the ways in which this gravity wave detector works is that it looks for the gravity waves that are being produced or shedded as they are falling in towards each other. We'll talk more and more about relativity and space-time and other things in the future, but I thank you for being part of this lecture.